Now we need to define the mesh interface. For this, we go to Mesh Interface, Create or Edit. The Mesh Interface panel will open. First, we enter the name of the interface in the Mesh Interface field. Now, we specify the two interface zones that comprise the mesh interface by selecting one or more zones in the Interface Zone 1 list and one or more zones in the Interface Zone 2 list. After this, we enable the desired interface option. Two options are relevant to sliding mesh: periodic repeats, when each of the two cell zones has a single pair of conformal periodic adjacent to the interface. This option is typically used when simulating the interface between a rotor and stator. We also need to enable coupled wall if we would like to model a thermally coupled wall between two fluid zones that share a sliding mesh interface. Then we click on Create to create new mesh interface. For non-periodic interfaces, Fluent will create boundary zones for interfaces which will appear under Boundary Zone 1 and Boundary Zone 2. If you have enabled the coupled wall option, then Fluent will create wall interface zones which will appear under Interface Wall Zone 1 and Interface Wall Zone 2. If you create an incorrect mesh interface, you can select it in the mesh interface list and click Delete button to delete it. After a mesh interface is defined, you can select the appropriate mesh interface and click the draw button to display the zones under Interface Zone 1 and Interface Zone 2 together as defined by the mesh interface. This is useful if you want to check the location of the interface zones prior to setting up the mesh interface. Next thing we do is to preview the mesh motion using the Zone Motion dialog box, which can be opened from the Run Calculation task page. From this, we go to the Run Calculation, then Preview Mesh Motion. The results, when we talk about the results of the sliding mesh problem, the same concept as any transient problem, we have to do post-processing same as any transient problem. Velocities are absolute velocities and vectors as well as contours, so keep that in mind. Now let us see the setup for dynamic mesh model. First, we go to the general section and enable the appropriate option for modeling transient or steady flow. We click on general section, then we click on edit. We go to the general section panel. Here we select the solver type. Velocity formulation is absolute, and most of the time the time step solver is transient. Then we go to cell zone conditions and boundary conditions panel. For walls, the motion attribute is set for wall zones, and we will not specify wall motion in the wall box. But we need to declare all walls as dynamic zones and specify the motion attributes in order for wall boundary conditions to be imposed correctly by the solver. Walls which move as part of the dynamic cell zones but are not declared as dynamic zones will not impose the correct boundary conditions. Next, we also have to check on cell zone conditions. We click on Edit, and for each cell zone we specify mesh motion. We have to specify the rotational axis origin, the rotational axis direction. We also have to specify the relative velocity as well as the translation velocity if there is. We can also specify zone motion UDF. Next, we enable the dynamic mesh model by clicking on dynamic mesh. We add data here. We can display the motion of the moving zones by prescribing motion to verify the simulation steps. Now let us see in detail the dynamic mesh panel box. There are various options in this panel that you can set in order to set up a dynamic mesh model. If you are modeling in cylinder motion, enable in cylinder option. If you are using 6 degree of freedom solver, then enable the 6 DOF option. If you want to have the dynamic mesh updated during a time step as opposed to just the beginning of time step, then enable the implicit update option. Next thing that we have to do is to select the mesh update method in the mesh updates box. If we are modeling a transient case, we can define events that will occur during the calculations. This we can select here. We have to go to dynamic mesh and then events as shown. Before starting the simulation, we should save the case and data files. Next thing that we have to do is to preview dynamic mesh setup in order to check whether the mesh motion is correct. For this, we can click on dynamic mesh, then preview dynamic mesh. We also have to specify the pressure velocity coupling scheme. PISO algorithm is recommended here for transient simulations. Mesh update methods are available in Fluent to update the volume mesh in the deforming regions which are subject to motion defined at the boundaries. We have three options: smoothing methods, dynamic layering, and remeshing methods. We can select any option of these, after which the mesh method setting dialog box will open, in which we need to specify various settings of the meshing methods or mesh update methods. So these are the selections that are available here, and click on settings. Let us see the smoothing methods in a bit of detail. First is the spring based smoothing. To enable the spring based or diffusion based or the Laplacian based smoothing, we have to enable smoothing options under the mesh methods. So we have to select this particular option and click on settings. The mesh method settings tab will open. In this, the first tab is of smoothing. In the spring based smoothing method, the edges between any two mesh nodes are idealized as a network of interconnected springs. We can control the spring stiffness by adjusting the value of the spring constant factor. The effect of spring constant factor is highlighted in the example figure. The figure shows the trailing edge of a NACA 0012 aerofoil after a counterclockwise rotation of 2.3 degree. And the mesh is smooth using the spring based smoother but limited to 20 iterations. Degenerate cells are created with the default value of 1 for the spring constant factor. You can get the original mesh distribution recovered if the spring constant factor is reset to 0. Let us see where to apply this spring based smoothing method. You can use the spring based smoothing method to update any cells or phase zones whose boundary is moving or deforming. For non-tetrahedral cell zones, the spring based smoothing is recommended when the following conditions are met. The boundary of the cell zone moves predominantly in one direction, and the motion is predominantly normal to the boundary zones. In these two conditions, we can use the spring based smoothing method. Next is the diffusion based smoothing method. In this, the mesh motion is governed by the diffusion equation with u as the mesh displacement velocity. The boundary condition for this equation are needed as inputs. The diffusion based smoothing is generally more costly than the spring based smoothing, but it also produces better quality meshes than the spring based method. The figure shows the mesh before and after rotating the boundary by 45 degree using the diffusion based smoothing. If you want to specify spatially varying diffusion, you can control the diffusion coefficient by adjusting the diffusion parameter alpha. A value of 0 implies the diffusion coefficient is 1 and uniform diffusion of the boundary motion into the interior of the mesh happens. Higher values of alpha will cause the mesh closer to the boundary to move with the boundary, and the boundary deformation is felt farther away from the boundary. In the example shown, an initially uniform meshed square domain is deformed by moving the left boundary to the right. Next is the Laplacian smoothing, which is the most commonly used and the simplest mesh smoothing method. This method adjusts the location of each vertex to the geometric center of its neighboring vertices. This method is computationally inexpensive, but it does not guarantee an improvement on the mesh quality, since there can be chances of poor quality elements. After that, we have the boundary layer smoothing method. This is used to deform boundary layer during a moving deforming mesh simulation. For cases that have a mesh motion UDF applied to a face zone with adjacent boundary layers, the boundary layer will deform according to the UDF that is applied to the face zone. The smoothing method preserves the height of each boundary layer and can be applied to boundary layer zones of all mesh types. As shown here, we have a initial geometry with its boundary layer mesh as shown in this figure. There is deformed compliant strip of this particular geometry, and using the UDF motion we have tried to retain the boundary layer mesh using the boundary layer smoothing. Next tab of the dynamic mesh settings contains the dynamic layer method. In prismatic mesh zones, you can use the dynamic layering to add or remove layers of cells adjacent to a moving boundary based on the height of the layer adjacent to the moving surface. The dynamic mesh model in Fluent allows you to specify an ideal layer height of each moving boundary. The layer of cells adjacent to the moving boundary is split or merged with the layer of cells next to it based on the height of the cells in the layer J. So the layer of cell adjacent to the moving boundary is split or merged with the layer of cells next to it, that is I, based on the height of the cells in the layer J. This is layer I and this is layer J, and this is the height H. If the cells in layer J are expanding, the cell heights are allowed to increase until H minimum is greater than 1 plus alpha times H ideal, where H minimum is the minimum cell height of the cell layer J, H ideal is the ideal cell height, and alpha is the layer split factor. We can define H ideal as an input. There are two options in this method: height based and ratio based. With the height based option, the cells are split to create layers of cells with constant height H ideal and a layer of cells with height H minus H ideal. With the ratio based method, the cells are split such that locally the ratio of new cells created is exactly alpha S everywhere. So this figure shows splitting of layers with the height based option, and the figure below that shows splitting of layers with the ratio based option. On zones with triangular or tetrahedral mesh, the spring based smoothing method is normally used. When the boundary displacement is large compared to the local cell sizes, the cell quality can deteriorate or the cells can become degenerate. This will invalidate the mesh, which will lead to convergence problems due to negative cell volumes. To resolve this, Fluent collects cells that violate the skewness of or size criteria and locally remeshes the collected cells or faces. If the new cells or faces satisfy the skewness criteria, the mesh is locally updated with the new mesh cells, otherwise the new cells are discarded. This is known as remeshing. Fluent has several remeshing methods like local cell remeshing, zone remeshing, local face remeshing, face region remeshing, cut cell zone remeshing, and 2.5D surface remeshing methods. All these methods can be selected in the remeshing tab. There are various parameters also for this that can be used as inputs, and this remeshing method can be set up for the dynamic mesh problem. So by that overview of the dynamic mesh problem, we have come to the end of this particular session. In this session, we saw details of sliding mesh, which is a subcase of the dynamic mesh. We also review highlights of how to set up sliding mesh and the dynamic mesh methods. This ends the session on sliding mesh model. Thank you for attending this particular session. See you in the next session of our lectures and our courses.